Sam has introduced. So first of all, good evening all. So as Sam has introduced, so we are looking at the integer factorization problem as of now, and the different ways that has been already identified in factorizing. So the one method that everybody is familiar of and everybody is talking about is the Shor's algorithm. The other approach is definitely the quantum annealing, which is also coming under the category called quantum adiabatic computing. So today what we are trying to do is we are actually looking at one of the papers, one of the implementations. Under quantum adiabatic computing also you have multiple ways of doing it. So today what we are going to discuss is actually something called QUBO model, which is actually quadratic unconstrained binary optimization model. So where we actually deal with like prime factorization multiplication. So you take the integers, multiply them, and you have a table generated there. So we work on the table and try to optimize it. So that is exactly QUBO model. So we will be looking into QUBO model, how it looks like. And again, this particular paper is actually trying to optimize QUBO model as well. So first we will have to understand the QUBO model a little bit to understand what we exactly is trying to achieve in this paper. So in QUBO model, so we will actually start with a normal integer integer multiplication. So this is actually a multiplication of 11 and 13. So here this is 11 and this is 13. Then you I'll actually represent it again once more. So this is your first integer and this is your second integer, and you are multiplying it and you have your carry. So I have it in my Jamboard here. So this is actually the normal multiplication that we see. So you have your prime integers, which is actually represented as the binary numbers, and then you actually multiply them, and this is the carry that is generated. So the important things we have to note in here is here we are actually the n is actually p into q. So important point to note there is always p and q are prime numbers. So when you talk about prime numbers are always of the form 1 and ends with 1. So it always starts with 1 and ends with 1. So here you have one optimization already done. So we can actually always go with the assumption that the starting and the ending is always 1. Now again, we are doing the multiplication. Now again, in the multiplication also here we can have this particular line will be always the first binary combination y. When this is 1, it is always going to be this one, and the last one is also going to be that the initial number that you are multiplying. Now again you are dealing with carries. So here we can say that here 1 plus 1 plus 1 is 1 1, that is 3. So here you write 1 and here you have the carry 1. So I believe this representation is clear to you. So that is how we have it in this particular table. So we look into this detail. So this is the same one. You have actually the representation here. So here you have P0, P1, P2 and P1, P3, and here we have Q0, Q1, Q2 and Q3. Then you are multiplying. So I have told the initial line will be always the first binary combination, because this is 1. When you multiply, you will get the exact one. So that is why we write 1, P2, P1, 1 again. Then we have the multiplication here, that is Q1, which we will multiply Q1 into 1. So we know that this is 1, so it is again going to be Q1. Then Q1 into P1. So that is how we generate this table. So these terms are called product terms. So from this row to this row, they are called product terms. So again, you can see that the last row is just the first value. Why? Because it is 1 into this entire value. It will be like this. Again, we have the column carries. That is what I have written here. So these are our carry terms. Again, we have the target values. So in the first section that we are talking about, what we are trying to do is we are trying to optimize this particular multiplication. So this multiplication process, we are trying to convert it into and optimize it. Now, why we are doing it? To understand this, we have to see how we can actually convert this into a optimization problem. So only then we can clearly understand this clearly. So here we have a optimization, factorization problem that we are trying to optimize. So here we have 5 and 3. So what we are doing is we are actually going with the assumption that the second number is always bigger. So we are actually taking and we have the 2's powers representation, right, in binary. So we are taking it as this variable and this particular variable representation, and we can definitely form this equation. So n is equal to minus p into q the whole square, which can be written. Now we will again try to minimize the combination here, and we can actually convert it into the minimal state. So what we are trying to simply achieve is that we are trying to predict the variables that can fall in here. And when we start with n, we can actually try to figure out what could be these variables, and thus we can actually understand it is 5 into 3. So that is how we have reverse engineered it, and we actually converted it into an optimization problem. So we actually generated this equation, and we are actually trying to fit into that equation with the minimum values possible. Lowering the minimal energy, finding the minimal energy state over there, which is again related to quantum annealing, which is already discussed. So that is why we are trying to do this. Now again, this can be further optimized. That is what we are trying to tell. So now what we are trying to do is we are having different levels of optimization. I have shown so many variables over there. So what we are trying to achieve here is we are actually trying to reduce the number of steps, the number of variables that we need to identify to solve this particular optimization problem. So here again, this is purely mathematical representations and notation. So just hope it will make sense. So what we are trying to do is we are starting with this table, and we are actually trying to find the carries and the product terms. That is what we have to understand. So we have to actually find these product terms and the carries and reach to this P and Q. That is our aim. So we have the target values over here, and we actually are trying to minimize the steps wherever possible as well. Now, again, how this paper is proceeding is that they actually started with P0 to P length, where the first and last bits is always 1, and this one also has the same assumption, and we can actually write the multiplication like this. Now again, they can be divided into columns. Okay, so that is one important thing. So what we are going to do is we are actually, these are individual columns over here. Now what we can do is for calculating the carries, we can actually convert, instead of treating them as individual columns, we can actually convert them into groups of columns as well. So what we are trying to do is we are actually trying to identify the number of columns that we can group in. So as per the previous paper to this paper which we are discussing today, we already have an assumption where, see here, here we have a multiplication table they have generated for 251 into 239. So for this particular scenario, here we could actually group it into 3. Why? Because the maximum possible carry value could be a digit of 3. Whereas in this case, the maximum possible value carry bits could be actually 2 only. So we could actually group it into columns of 2. Whereas in the other scenario, it could be 3. So depending upon the number of bits, when you're considering for the carry values, for the maximum number of carry value bits that you get, you can actually consider group it into columns and then evaluate. So you can actually look into individual columns, not exactly these columns as we usually do. We can actually group them and proceed. So that is the first assumption we are going in. Now, again, this particular column don't need much of the calculation. It is always going to be 1. So we can immediately neglect this one. Simply need not do. And this also will be immediately 1. We can actually skip those two. Again, the only thing what we should be worried about is the intermediate thing. And we are trying to find out P2, P1, Q2 and Q1. So that is our assumption. I mean, that is our target. So again, now what we are trying to do is we are going to find out what are the variables and how we will represent. So now currently the first step is going to we are going to focus on the carry variables. So now the carry I have written here, these are the carry variables. Now how they have named it is, see, I have already told we are dividing it into columns. The column numbers based on the maximum carry bits that can be generated. Now it is divided into, this will be the first column, 2 raised to 1 and 2 raised to 2. This will be the next column and this will be the next column. Now this value will be the column 1's first bit and this will be column first second bit carry. So this is one column. So this will be column 1's second bit and this will be columns 1's first bit. So that is how they go. And this will be column 0. This is column 1. This is column 2. Now, see, please, rather than thinking it mathematically, let us talk in normal sentence. So what they are simply trying to achieve is, here they have, we have a normal way of doing the multiplication, which is like this. Okay. So what we try to do is we actually converted it into the table, and rather than going with the previous way of simply putting in the x square x2 like that and trying to optimize, we actually eliminate more variables. Hope you understood. Like in this particular approach, where you are simply substituting some values and trying to find out the entire variables, you have more variables that you're trying to evaluate. Now here we are restricting it to simply this P1, P2 and Q1, Q2 alone, rather than like let's say 4 or 5 variables. Here we have reduced it to just 4 variables. So that is what we are trying to achieve. Like when we actually convert it into the multiplication table and look at the number of variables, we have these 4 variables that we need to understand and these carry variables. Now again, when we look at the carry variables, we can actually treat the product terms individually and the carry terms individually. Now that is what our second target is. So what we did is, first we started with the multiplication table. We identified the variables that we could use to optimize. That is actually the different variables we identified, whose values we have to predict. Now again, what we are trying to do is we split it again carry variables, which could be treated again differently. Now in the carry variables, we are trying to again. So towards the end, you will see that we need not even find these two variables. We are eliminating them also. So that is how we went in. Now again, going to the equation part. So for each block we can actually find the product. So it is nothing but it is the sum of this entire thing. Okay. These are the product terms. So the product for this complete column can be called as the sum of these ones. So that is what is written here. It is the sum of all those. Now again, a carry is again for that particular column is again the sum of those carries. So why we are doing it is, we need to understand the maximum carry variable bits that we have to assign there. So we know that the maximum product, the maximum number of, so looking at this, we can understand like what could be the maximum scenario of carry. So here the maximum possible carry could be the case where we have 1 here also. So it is 1 plus 1 plus 1 plus 1. So that is exactly what they have written there. So maximum carry possible is when we have the maximum product and maximum carry function. So where we have the maximum here as well as the maximum here. So in the product terms also you have the maximum, and in the carry value also you have the maximum. That is the maximum case we can have. So that is exactly what we have. Now if the maximum carry is 0, then we will assign the maximum carry numbers as 0. So we need not assign anything there. Then again, if it is not that, then we will actually go to the seal of maximum carry plus 1 to the carry numbers. So hope you got some idea what we are trying to achieve. So again, to give some more idea to before moving to the next step. So what we are going to do is we are actually trying to convert the factorization problem into an optimization problem. So optimization problem, you all know that it is trying to minimize something. So minimize actually some energy difference or something like that. So when you actually convert it into quantum annealing, that is what we are trying to achieve. Now again, we actually we have different ways of doing the prime factorization. That is simply multiplication. We can actually convert it into multiplication, where you treat them as binary variables, where each variables are considered as individual x2, x1, x3, and simply substitute it, and that then you can optimize it. Now what we try to do is we actually convert it into the QUBO model, where we can actually again reduce the number of variables that we need to find out to reach onto this P and Q. And now in this paper, we are actually again trying to optimize the number of variables that we need to evaluate. So that is what we are trying to achieve. And this is actually the equation for the carry numbers, the maximum carry numbers bits that we are going to generate. So again, this is not something that we are developing. We could have a lot of improvements that is that could be coming in your mind also, like right now when we are discussing this. That is actually the aim of it, like to have a discussion of this paper and find out where we can actually improve it and put in our contributions in there. So that is about this section. Now again, we can see how we can actually improve this and eliminate these variables from the evaluation, like how we can actually achieve the same result by eliminating this one. That is the optimization, one of the optimization that we are targeting. So hope that is clear.
Yeah.
Any doubts?
Nilay, Kedhar.
Hi.
Hmm.
So I'll stop sharing.
Okay, Mahima. Yeah. All right, Nilay. Nilay, you're muted, by the way.
Yeah, is it visible?
Yes.
Yeah. So, as Mahima laid down that instead of trying to solve factorization problem using the Shor's algorithm, we are trying to go look out for other alternative paths. So one search was using the QUBO model converted into a multiplication optimization problem, and then with quantum annealing we could have done it. So there were many ways there were improvisations can be done in the given algorithm which was proposed. So there were majorly two issues when you were actually trying to find the maximum carry function, such that there was no constraint based on the target value. So which meant that you didn't have an upper carry, like the maximum value, like the upper bound up to which you need, because you need a calculation so that you can accordingly have so many number of qubits to solve, but you didn't have any dependency upon the target value, so which led to that upper carry bound value to be larger. Then there was another, like the optimization problem, where regarding the maximum c in for the function, which means like the maximum carry input which you can get in the next iteration. So that says that the maximum value that can carry into the columns increases the complexity model. Like it's because the more carries will be coming in, so there'll be like more variables will be there, and that will actually increase the complexity because you'll have more and more of variables to solve. Then it says that the maximum carry value is smaller than the maximum value of C in. Yeah. So if you're going, mhm. Yeah, so it said that suppose for an example, if the maximum value for columns I, like given any one among the column, like which means coupling them, any one among the column, such that it shows it denoted by the C maximum sane function is denoted by 20 times the 1 and 2 power 1s. You're thinking that both the bits are 1, like both the carries are 1 because it's going to be maximum carry in for the next iteration. So that would suggest you will have this function value as 3, which is larger than the maximum carry of value of 2, because you can have 2 carries maximum, that is why dividing the columns, splitting them into groups of 2, but the maximum function's value, it corresponds to 3, so it was an additional thing which we need to optimize because we would have needed an extra qubit to do it. Then secondly, which the proposed method which they did was that it said that the scene value denotes the maximum value that can carry into the columns, and it's initialized actually as 0. Then it said that blocks column 0, which basically means this particular 2 power 0 column didn't need any carry variable because we already knew it was going to be 1 always. So we took it at pre-assumption. So we decreased the extra qubit which we needed over there. Then supposingly it said that if we know the number of carry variables needed by column 0 to column I minus 1. So given that you want to find out up till 2 power 4, so you need to calculate how many maximum carry variables you actually need. Even if we know by this like how many carry variables we need, then depending upon that we can calculate the maximum number of carry variables which will be required for the ith column. So like it's like when you know for the first column how much it needs, when you know for the second column how much needs, and then when you know for how much third, so you can develop a progression, you can see the pattern how it's actually going, and then you can correspondingly calculate for the ith column how much maximum carry it would need. So they gave it this that the maximum product is equal the product, that means summation of all these products individually that corresponds to the sum. Then like this typical math multiplication how we do, we vertically add all the segments and then take the carry to the next segment, vertical one. So we take the product f5 plus the carry, then divided by the splitters, such that that this is the maximum value. And like this is very proven over here that your maximum carry value can be 2, but the function's value of the maximum carry coming in is 3. So such that, and second to do with optimization is to, when like as Mahima told, that we need to decrease this number of variables to, so that, so the only way like in one such way is like when you have more variables coming in, you try to find in the relation between them, so you can omit one of them. So it said that if two vertical, it said that if two different column blocks have the same width, which means that they have the same number of bits representation, then the ranges of the corresponding product function have similar properties. So which basically means that the function which you're trying to deduce over here, if the different columns, like supposedly 2 power 1 and 2 power 2 are grouped together, and 2 power 3 and 2 power 4 are grouped together, so if they have same number of width, which basically like a number of bits are same representation, so that means there is a relationship between the product fi function for this particular group and for this particular group. So we can deduce a relationship between them. So when you have the relationship, relatively becomes easy to solve the optimization problem, because suppose you have 3 variables and you know the relationship between 2 variables, so you can replace the third variable with the other relation. So technically we'll have 3 variables, but since we know the relation between 2 variables, we were able to be reduced it to 2 variable problem. So we decreased 1 variable cut out. So similar pattern over here. So if we know the said that these two groups, like if 2 power 1 and 2 power 2, the size of this group, the product function size, and the size of this particular group is almost same, that means there's a relationship between them. So we can bring in the relation, and we can reduce the number of qubits which we actually need. So that was a one other optimization which we did over here. So after doing that, they derived the carry number, which is the maximum carry variable they wanted. So then they updated like from the equation 4 over here we had such that, and then uh, we update the C in value, that is the incoming value of the carry, to compute the carry num function. So we know the value we have got over here. So we put it in this value, the maximum carry function over here. Then then we calculate the k max, that is nothing but the like the number of bits which is required over there. Then you have the C in value getting updated, like C in is equal to C in plus the additional thing coming up. And that is then we are able to, like, since we developed a relationship between the maximum carry which was already there with the carry numbers, but we didn't have in much relationship between the C in variable, like the coming a variable. So with relations with an assumption that the product function with the same, we were able to bring in the relationship between carry in value and with respect to the carry number and the maximum carry function. So with that, we were able to deduce the final equation, which said that C in value is equal to, in terms of maximum carry. So in short, we were trying to deduce the number of bits we actually require over here. So with this optimization, where you bring in the VWAT in the relationship, and we modify the maximum carry with the seed, and then again brought into with carry num. So we, with the relation, we were actually able to reduce the number of bits we actually required to solve this. So that was like the improved carry number variable computation. Yeah.
Hmm. Awesome. So, Kedar, you want to continue?
Yeah.
Ah,
Right.
all right.
Okay. So after doing all those optimization, like Nilay and Mahima told, the main purpose of these optimizations are to decrease the number of variables. So the more the number of variables we have, it's like instead of optimizing, if we have just the variables that we started with, then obviously we will not be able to achieve it in even in quantum computing's perspective, because the number of qubits and the computation complexity will be too high. So the last step of optimization here is to replace the unknown P1s and P2s. So uh, just a minute. Like um, like we started with this problem, and if we take this problem, so here we have four unknowns, right? P2 P1 and Q2 Q1, because the other constraints are put, and these ones are already in place. So just by going with the initial problem, we would have four carry variables. Like Mahima told, we will be at the end optimizing these last two, I mean these two carry variables. So uh, this is the last step for that. So here what we do is we basically replace P1 and P2 based on the target values of, at the end. So like uh, if we take this as column 0, and like Mahima told, this as column 1, and this as column 2, then in column 1 we have the 0 1 as target variable. So that's what we call target variables, the our number that we want to factorize. So this will be the one here will be target variable, sorry, target value of 1 1, and this would be target value of 1 0. So using these, we just use this rule as a rule to replace the P1s and P2s into Q1 XORed with target value 1 1, and P2 as Q2 XORed with target value 1 2. So here P1 is the smaller, I mean, we start with the problem and define P1 to be the smaller integer, and I mean, sorry, P's to be the smaller integer and Q's to be the larger integer, and the product of which is our problem number n. So the first two, I mean, this. P1 and P2 bits of the smaller integer is being replaced by this, and if target value 1 1 is 0, then we would have this particular um, format. That, I mean, if you want to write it in that format, then if the target value 1 1 is 0, then we would have P1 as nothing but Q1, and if we have target value as 1, then anything XORed with 1 is the complement of that, the negation of that. So we would have P1 as 1 minus Q, depending on the problem. So what I mean, as any optimization, this is also just a way of decreasing the unknown variables. But what it does is it also increase the identical terms, right? So like how Nilay was explaining the method to limit the range of coefficients or the carries here. So instead of taking the max carry value as 3, we should take it as 2. So when we have identical terms, we have a better way of predicting the limits. So and like as I told before, this reduces the complexity, and in terms of simulation, it also increases the accuracy of it. So that was the last step.
Wow. Okay. That's pretty good. Okay, great. Um, so before we move to the next part, Mahima, I
Yeah.
sure? Yeah, yeah. So, what's the ideal path for us next?
Like,
No, so now we have completed this paper. So the next paper is the noisy qubits one. Are we gonna go with that, or go to the 2020 paper of the same one, or get into the implementation of this?
I think,
yeah,
okay, sorry.
yeah.
Huh.
Please tell.
No, I mean, I was just saying that I think we should probably first implement this once,
Right, right.
or at least have a illustration with
Okay,
various numbers. Maybe in the paper they have mentioned some set of numbers with which they have factored
right.
with this methodology. So if we try to illustrate it,
Okay,
then we would have a very clear understanding of that.
okay, okay.
And of course, the noisy qubit one is the next natural step. This is just an intermediate, or probably like for a self
Right,
learning thing.
right. Okay, great. Anyway, Vaibhav is looking into that. So whenever he's back, his implementation he'll show us, right? So that should accelerate our learning,
Yeah.
right? Huh.
Yeah.
Okay.
Yeah, I interrupted. Mahima, you have to say.
Yeah, Mahima, you were saying?
No. That is actually a good step to take. Actually, I mean,
Okay.
like I mean, once we implement and see it running, we'll have a good understanding of how it goes and what could be the other constraints we have to look into.
Mm-hmm.
So, yeah, that
Okay.
is actually a good step, and definitely we'll have to look into the other papers as well.
Huh. Yeah. So implementation and then the other papers, right? Okay.
Yeah. So the reason paper in this area
Mhm.
should also be analyzed. Like,
Right, right,
yeah,
right.
when we are implementing it,
Hmm.
we have to look into that because we might spend unwanted time on optimizing something which is already optimized.
Right. Okay.